Okay, let me just have a look at the chat box if there are any questions. Okay, fine. So, what we have discussed so far, we have actually taken into account only the classical nature of electrons. By classical nature, what we understand is electrons will follow the Newton's laws of motion, right? That is the uh, underlying assumption through which we discussed whatever we have discussed so far in chapter 2 with respect to electrical conduction as well as thermal conduction. Now we will look from a perspective of quantum mechanics because electrons can behave both like a particle as well as a wave, right? So now we will discuss the things which are which can be explained only by the dual nature of electrons, right? So let us start with molecular orbital theory of bonding. Some part of it, and you might have had a look at it before also, but let us just recap it because this will be the basis for many things which we will cover in this chapter. So for to discuss this molecular orbital theory, let us take two hydrogen atoms. We have, let me get my pointer. Yes, so we have two hydrogen atoms. In the initial, like in the beginning, they are separated by a distance, like they are at infinite distance from each other, they are not interacting with each other. Okay, so in that case what will happen is the wave function of, I hope, okay, let me just introduce the concept of wave function also. Wave functions in quantum mechanics, wave function is the most fundamental property of a material. You can derive any property of a material using the, if you know the wave function of that particular material. Okay, and each electron has its own wave function, right? The physical, if you want to interpret wave functions physically, what you can say is that the probability of finding an electron at a particular time and at a particular uh, place, that is defined by the wave function. Actually, the amplitude of wave function, basic mod of psi. Let us say if wave function is psi, mod of psi. Let me write it here probably, that will be better. Probability of finding an electron, that is defined by mod of psi x comma t square, right? This is the probability of finding an electron. This is the physical interpretation of wave function, right? So now let us start our discussion. We have two hydrogen atoms. They are at infinite distance from each other, which means they are not interacting with each other. In that case, their wave function look somewhat like this. You can see here r is equal to infinity. When they are at infinite distance, then their wave functions look somewhat like this. Like basically at their center, the probability of finding them is maximum, and then as you go away from from the position, the probability of finding the electron basically becomes zero. At the atom center, the probability is highest, and then the basically the it decays as we go away from the center of the atom. What happens when we bring them closer? Let us say if we bring them closer, then what will happen? These two wave functions, they will start overlapping with each other, right? They will, basically the atoms will start interacting with each other, and atoms interacting means the electronic wave functions, they will also start interacting with each other, right? So because of this interaction can be in different ways. It can be because these are two waves, right? Then their interaction is possible in many different ways, and two particular ways in which we are interested in, actually they can either interfere in phase, which means their wave functions will add to each other, right? So that means they are interfering in the constructive manner. If they are out of phase, then the resulting wave function will be the difference of these two wave functions, psi 1 minus psi 1 as ra minus psi 1 as r v, right? Why this, what is this 1s? Because we are discussing the hydrogen atom, right? So the hydrogen will have only one electron, which will be in the 1s orbital, right? We can also say actually that there are two atomic orbitals which are coming together and they are interacting with each other, because there will be one atomic orbital here with one hydrogen, and there will be another atomic orbital with another hydrogen. So these two atomic orbitals are coming together and they are interacting with each other, right? And they can interact in two different ways. One is in phase, another one is out of phase, right? When they are interacting in phase, then you can see that the density of electron is maximum, or probability of finding an electron in the center of the two atoms, that is maximum, right? While when they are interacting in a out of phase manner, then the probability of finding an electron in the center is almost zero actually, right? So this is the difference between in phase and out of phase interaction or interference. And because of that actually they form bonding and anti-bonding orbital. As you remember, right, when there is bonding, the electron density is maximum at the center of the two atoms. So that's why this orbital, this molecular orbital which is formed from two atomic orbitals, that is known as bonding molecular orbital, and the other one is known as anti-bonding molecular orbital, right? These two atomic orbitals, these two molecular orbitals, they have different energy and wave function. You can see the shape of the wave function here itself, it is actually quite different. In and when they have different wave functions, of course their energy will be also different, because you know from Schrodinger equation that h psi should be is equal to E psi. This is the Schrodinger equation, right? So from here we can say we know that energy also depends on the wave function of an electron. So if they have different wave functions, naturally their energies will also be different, right? And what happens is that, I mean, we will see in the next slide actually, but the energy of bonding molecular orbital is much less in comparison to anti-bonding molecular orbital. So of course electrons will prefer to go into the bonding molecular orbital, right? Because any system wants to go to the lower energy state, because this bonding molecular orbital, it has lower energy. The electrons will pair up their spins. There will be two electrons coming from each hydrogen, right? One electron from each hydrogen atom. So there will be two electron, total number of electrons will be two, and they will basically pair up their spins and go and sit in the bonding molecular orbital. They will occupy the bonding molecular orbital. That is what we can see in this picture also here. What is happening in this case is, so when the two hydrogen atoms, when they are coming and interacting with each other, there can be different types of contribution to the potential energy. The positive contribution to the potential energy, it can come from electron electron interaction as well as proton proton interaction, right? Because they have similar charges, same charges, right? Then negative contribution can come from electron and proton interaction. Only from electron and proton interaction we can have negative contribution to the potential energy. What happens in case of bonding molecular orbital is actually this negative interaction which is coming from electron and proton interaction, that is stronger in comparison to anti-bonding molecular orbital. Why? You can see from this picture here, right? Because the electron density is highest here at the center of the atom, and when the electron density is higher at the center of the atom, it will have better interaction with the nucleus, right? With both the protons. The electron at the center, they can have interaction with both the protons here, in comparison to when you have electron here, then the negative interaction will be less in comparison to this particular configuration when the electron is at the center. Because of this, we have basically this uh, lower energy lower energy in case of bonding orbital, because we have higher contribution of negative potential, right? Energy of, and you can also derive this, and you might have seen this curve, I think, in the first chapter also, that actually this bonding orbital, this bonding molecular orbital which is getting formed, that has a minima. There is a minimum energy. It passes through a minimum which is lower than the initial energy of the electron. Initially, both the electrons had energy which is E1s, right? Because they are coming from 1s orbital, atomic orbital, right? So their energy, both the electrons had same energy, and it was higher than the bonding molecular orbital, the energy of the bonding molecular orbital, right? So ultimately, because of the bonding, the energy of the system, that is actually getting lower, right? And any system would like to have lower energy than the original configuration. So here we are able to reduce the energy of this configuration from E1s to E sigma, right? Basically the energy of the system is going down. That is why actually this bonding is energetically favorable, right? Naturally, in nature we know that every system wants to decrease its energy, and when the energy is going down, the process is energetically favorable. That's why this bonding is energetically favorable. From this plot we can also say that what is the bonding energy. Bonding energy, basically it will be the difference of these two energies, right? The energy which is energy of two isolated atoms which is there, which is this energy, minus the energy of bonding molecular orbital, right? So this will be the bonding energy, right? You can see this here also. Bonding molecular orbital is the difference between the energy E1s and E sigma a, right? So what happened in this case is that initially we had only one single energy level. There was only one single energy level, right, which was E1s, or there was only one atomic orbital. One atomic, by one atomic orbital I mean is that the energy level of both the atomic orbitals was same, right? And now what happens is that we have formed two different energy levels. One is this bonding molecular orbital, this is one energy level, and another one is anti-bonding molecular orbital. Although it is not occupied, both the electrons have occupied only the bonding molecular orbital, but we still have, I mean basically we have also formed another molecular orbital which has different energy. So we have actually splitted one single energy level into two energy levels, right? Initially, we had one single energy level that gets split into two energy levels. This is also known as splitting of energy bands, right? There was a single energy band which was E1s, and now it has gotten split into E sigma and E sigma star, right? This is called the band splitting, or the splitting of energy band, right? Any questions so far? Let us have a look at this case of helium also. In helium we have two electrons, right? We have two electrons from each helium atom. So both the electrons are in the 1s energy level, right? 1s atomic orbital has two electrons in case of helium. So what will happen when they come closer to each other? They will also start interacting with each other, and as a result of that we will have two molecular orbitals. One will be bonding molecular orbital, another one will be anti-bonding molecular orbital. This will be the bonding molecular orbital. Lower energy one is always known as bonding molecular orbital. This will be anti-bonding. Once these molecular orbitals are formed, we need to now rearrange these four electrons, right? So first two electrons, they will pair up their spins and they will sit in the bonding molecular orbital. The next two electrons, they will go and sit in the anti-bonding molecular orbital. So now if you look at the energy of final configuration and compare it with the initial configuration, you can see actually that the final energy is higher than the initial energy, and that is why this bonding is not energetically favorable. That's why you will never see this helium 2 molecule, right? Although we have H2 molecule, because we saw that this is energetically favorable, we never have this helium 2 molecule that is not energetically favorable. And the reason for that is because the final energy after the bonding, it is higher than the initial energy of two isolated helium atoms, right? Any questions so far? If anything is not clear,
Sir,
yes.
sir, in the diagram, the bonding diagram, bonding and anti-bonding molecular orbital,
Mm-hmm.
you use the term in phase and out phase, na?
Nah.
So I'm just asking that outphase, the physical sense of outphase is that both the electrons are simultaneously moving apart from each other. Electron means electron clouds.
Uh-huh.
Then only the probability can be zero at that point.
Right, right.
So if the electrons are moving out of phase,
Mm-hmm.
then probability is zero. Then if you say the case of helium, na,
Mm-hmm.
so I know helium is not possible,
Mm-hmm.
but they are showing two electrons in bonding and two electrons in anti-bonding.
Mm-hmm.
So is it like that that one electron of one helium combines in phase with one electron of one, means the electron cloud, one electron cloud is coming simultaneously towards each other and another electron cloud is moving simultaneously away from each other. Then only they can go to the anti-bonding now.
Mm-hmm. Okay.
So I'm just confirming it. They are, is that this in phase and out phase signifies that they are electron clouds are simultaneously coming and going
Okay.
apart from each other.
Okay. So basically, what will happen is that one electron from each helium atom, right? They will be in phase, right? Because they are in the bonding molecular orbital. That means they will moving in phase. But at the same time, we also have two electrons which are moving out of phase also, right? You can probably imagine in phase and out phase in this way. Let me just plot it here. I want to clear this. Let me just give me a second. Yes. So now if we look at this, in phase means basically the electrons, they are moving somewhat like this. So basically both the electrons, they are reaching at the center of the bonding at the same time, right? That's why we get this higher uh, higher sorry, density of or the probability of electrons, right? Basically the movement is somewhat in the shape of 8. I think they move basically like this, right? One electron moves like this and another one is also moving like this. So and they reach at the center of the electron, center of the bonding at the same time. Out of phase means basically that they will be moving somewhat like this, like they will they will not reach the center of the bonding at the same time. When one one is at the center of the bonding, the other will not be there, or actually it will be moving in the opposite direction. So ultimately the 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 density of electrons at the center of the bonding will be zero. What will happen in this case, in the case of helium, is that there will be two electrons which will be in phase, like they will be moving in summation. Basically their wave functions will add to each other, while at the same times we will also have two electrons which are out of phase, right? So ultimately the overall configuration which is getting formed by these four electrons, that will have higher energy. As you can see, actually this will be the energy will be the total of all these four electrons, right? So this is lower than the initial configuration, this is higher, but ultimately the energy which we will get of the four electrons, that may be slightly higher than the initial configuration energy. So that is why this does not become energetically favorable. I guess your question was that will they be in phase and out of phase at the same time? So the answer to that question is actually yes. There will be two electrons which will be in phase to each other, but at the same times there will be two electrons which will be out of phase also. Okay, and because of that the final configuration will have higher energy. Is that
Okay, sir. Got it, sir. Got it, sir.
yeah? Okay. Any other question? No. Okay. So then now let us try to apply this molecular orbital theory to the formation of solids. So what happens in solid? Like we have n number of atoms which are coming together, and this n, the number n, like number of atoms, this can be of the order of Avogadro's number, right? This can be 6 point, like out of the order of 10 to the power 23. So we have large number of atoms which are coming together and forming this solid. So let us look how this can be explained using this molecular orbital theory. Just now we discussed two hydrogen atoms coming together, the case of two hydrogen atoms coming together. Now let us see if we have three hydrogen atoms. What will happen if we have three hydrogen atoms and they come and start interacting with each other? So what will happen? Initially, we had only two molecular orbitals. In this case, we will have actually three molecular orbitals because there are three atoms which are coming together, and they can interact in different ways. For example, this is totally symmetric or the lowest energy configuration, lowest energy interference of the wave functions. Then this is psi b, which is somewhere in between. Actually, this is the antibonding completely. This is the highest energy where there are alternating signs. So one thing which you can remember is that out of phase, completely out of phase of the highest energy configuration will be alternating signs of plus and minuses, which means all the wave functions are completely out of phase with respect to each other. This will be somewhere, this psi b is somewhere in between. One thing actually before that we need to remember is that total number of molecular orbitals is equal to the total number of atoms which are forming the bond, right? But if you have like n molecular orbitals, that means they can occupy 2n electrons, right? If you have n molecular orbitals and each molecular orbital can have 2 electrons, that means the total electrons which can be occupied in n molecular orbitals, that is 2n, and that is also known as electronic states. So we say actually that by the interference of n atoms we will have n molecular orbitals and 2n states of the electrons. 2n states means there can be 2n electrons which can be occupied in the n molecular orbitals, right? So here we can say that there are three atomic orbitals. They will form as a as a result of interference of these three atomic orbitals. We will have three different molecular orbitals. One of them will be completely in phase. One molecular orbital will be completely in phase, which will be the lowest energy one, and the others will be slightly out of phase, or somewhere in between. And finally there will be also one configuration where all the atoms will be, sorry, all the atomic orbitals will be out of phase, completely out of phase, right? And what will happen? So now we have three electrons. We have already found three molecular orbitals. If we want to fill up these molecular orbitals, first molecular orbital will be filled by two electrons. They will pair up their spins and fill this lowest energy one, and the third electron will go to the slightly higher energy level, right? And because of this, the energy of this H3 molecule, if you let us say if we want to form H3 molecule, the energy of the H3 molecules will be higher than the energy of H2 molecule, right? Because H2 molecule had both the electrons in the lowest energy level, and that is why H3 is much less stable than H2, right? The molecule we very rarely see H3 molecule, but H2 molecule is very stable because of this energetic considerations. The formation of H2 molecule is energetically favorable. Okay. What will happen in case when we have n atoms? Let us say now we want to form a solid of lithium. We want to form solid of lithium, which means there are n number of lithium atoms which are coming together and they are trying to form bonds with each other, or basically they are interacting with each other. For bonding is basically sort of interaction with each other, right? So we have n number of lithium atoms and they are coming together and interacting with each other. First of all, let us look at the electronic configuration of lithium, that is 1s2 2s1. That means there are two electrons in the 1s energy level and there is one electron in the 2s energy level. Because this 1s2 level is first of all, it is full, this shell is completely full, and also it will be very close to the nucleus. This will be the shell or subshell which will be the closest to the nucleus. It will not participate in the bonding, right? This atomic this energy level E1s, it will not participate in the bonding because first of all it is full, and secondly it is very close to the nucleus. That is why there is it is already stable, so it will not participate in the bonding. Only the 2s energy levels or the electrons which are in the 2s shell or subshell, those will participate in the bonding, right? So what will happen when we have n atoms? There will be overlap of n energy levels or n atomic orbitals, right? If we have overlap of n atomic orbitals or n energy levels, we will form n molecular orbitals also, right? As we have seen already, there will be n different energy levels or n molecular orbitals. Right now, actually, when we are discussing about solids, I think I will use the terms energy level rather than molecular orbital, because it becomes a little bit confusing in solids. Like for example, in lithium, we don't have really a molecule, it is a complete solid which is getting formed. So right now, I mean, from now on, when I use energy level, basically that means that is more intuitive. In case of solids, we have n different energy levels which are coming from lithium, sorry, n energy levels which are at the same energy level, right? And lithium atoms, they all have one electron in 2s. So these n atoms are coming together and interacting, and because of that we will form n different energy levels, right? And then because of that, there will be splitting, right? One single energy level that will get split into n different energy levels because of the formation of n different energy levels, right? And typically this energy splitting is of the order of 10 electron volt, which means this distance or this level in the energy, this is typically of the order of 10 electron volt. In this 10 electron volt, we need to accommodate basically n energy levels, and n is the order of 10 to the power 23. N is of the order of 10 to the power 23. So we are forming energy 10 to the power 23 energy levels in a energy difference range of in a energy range of 10 electron volts, which actually means that for all practical purposes, although they are discrete energy levels, they are actually sort of continuous, because the energy difference between two consecutive energy levels will be very very small. So for all practical purposes, we can say that these energy levels are sort of continuous, and that is why it can also be called as energy band. Rather than calling them different energy levels, we can call them energy band. Actually, we can call this whole thing, whole energy splitting range, as a energy band, right? What will happen is that, because there will be n electrons, right? There are n atoms, that means there will be n electrons, and they will be occupied in n by 2 energy levels, right? Because each energy level will have 2 electrons. So all the electrons will be occupied in n by 2 energy levels. So n by 2 energy levels will be occupied, but there will be n by 2 energy levels which will not be occupied, which will be empty. I think there is a question somebody is asking: what exactly is the difference between energy level and states? See, each energy level can have 2 electrons, and basically we say that these two electrons are two different states. So if you, actually let me repeat the question. Somebody is asking, what exactly is the difference between energy levels and states? So energy level, what we call energy level is this one line. Actually, this is one energy level, right? This is one energy level, but in this single energy level we can have two electrons. And state is actually more sort of the overall description of an electron. Like for example, in these two electrons, everything else will be same, only one thing will be difference, which will be the spin. These two electrons, they will have opposite spins. Rest of the other parameters, like you might have heard about KLM and different I think orbital numbers, or I don't remember the name of that thing, but like all the numbers are same, only thing is that spin spin quantum number, actually that is different, right? So in some people are asking questions about tutes. This is not the right time for asking question about tute. If you have any problem with respect to tute, please, you can ask them later on. Uh, all right, where was I? Yes. So this is one energy level, and one energy level can have two different states because there are two different electrons. The difference in these two electrons is only the spin quantum number, which will be not the same for the two electrons, right? Okay. So what I was saying is that there will be n by 2 energy levels which will be occupied, and there will be n by 2 energy levels which will be empty, right? But this energy band is more or less continuous. We will see that in the next slide also. Like, so far we were discussing only the 2s energy levels, 2s orbitals interacting with each other and forming a 2s band. This is the green lines. They are representing actually the molecular orbitals or the energy levels which are formed by 2s electrons. But there can be actually, there will be also 2p energy level, 3s energy level, that will also be there in lithium, right? They will also overlap, and similarly they will also form the different energy levels, right? As lithium atoms are brought together, the atomic orbitals overlap and give rise to bands. So we will have 2s band, although there are no electron in 2p, but we will have, I mean, there will still be interaction between the empty 2p energy levels, right? So they will form a 2p band. Similarly, there will be a 3s band which will also be formed. Bottom of the 2p band, in this case, we can say that we can also see actually that the bottom of the 2p band, which is these, like, light blue lines here, this band actually which I'm noting here, the bottom of this band, that is overlapping with the top of the 2s band, right? So bottom of the 2p band, that is getting overlapped by the top of the 2s band. So there is a certain overlap of the two bands. So there is no that also means that there is no energy gap between two different bands also. Like if one electron wants to go from 2s to 2p band, it does not have to really jump a long distance. It can just go through these continuous energy levels, and ultimately it will reach in the 2p band also. So basically, this electron can go all the way up to vacuum level, where it will become actually free. The potential energy of this electron will become free. Basically, if electron goes into the vacuum, or in the free air, that means the potential energy of the electron will be zero. So this electron, which is, let us say here, that can go all the way up to the vacuum through these continuous energy bands. In some materials, you will see later actually these bands are not continuous, so there is a gap between two bands, which means, let us say, let me just explain one more concept here. Let us say this is my one band here, this is one band, and another band is getting formed like this, right? Which means there are no energy levels in this gap here. If there are no energy levels, electron can never be in this region here. Either it has to be here, or it will be here actually. So if it wants to go from this band to this band, it will have to make a jump. So this, it will have to have certain amount of energy, only then it will go from one band to the other band, because there are no allowed energy levels in this gap here, right? But in case of metals, we don't see that, because what happens is that we form a continuous band from, from the in levels which are occupied up to the vacuum level. So if an electron has to go from one state to another state, it can go very easily, because the energy levels are very close to each other, or they are basically continuous. Okay. So we can also say that instead of forming different bonds, we actually have a single band. This is a single band because there are no energy gaps between the energy levels of different bands, right? So in case of metals, we see this, typically we see this kind of overlapping of the bands, and that is why actually the band configuration of metals is also sometimes represented by this kind of figure, where you can see actually there is a 2s band, this is a 2p band, and this is the 3s band. The bottom of the 2p band, it is overlapping with the some part of the 2s band. Similarly, bottom of the 3s band, it is overlapping some part of the 2p band, right? In 2s band, half of the orbitals, half of the energy levels, sorry, again, sometimes actually I'm mixing the two terms, but these are actually energy levels. So half of the energy levels, they are occupied, and half of the energy levels, they are not occupied. You can probably, you can see that, you can sometimes say that in the picture it should be half, but that is not the case actually. These energy levels, they are not equi spaced from each other. So although we can have actually half of the energy levels in this much energy, and rest of can be in the energy range can be less for the rest of the half. I mean, rest of the orbitals or rest of the energy levels, right? So these half of the energy levels are in 2s band. They are full, and rest all are empty, right? Electron energy is basically it will increase as we go up, right? Finally, when the energy of an electron becomes zero, that means it has gone into the vacuum level. It has become a free electron. Okay. Any questions so far, like whatever we have discussed? Because these are some concepts which may not be very intuitive. So you can think what we have discussed so far, and if you have any doubts, you can ask them now.
Sir? Excuse me, sir.
Yes.
Sir, lithium has 2s1 orbitals. So, sir, do the 2s1 orbitals
Yeah,
combine to
your
give?
voice is very low. Actually, can you be a bit louder, closer to the mic?
Sir, am I audible now?
Yes, yes.
Sir, as lithium has an like one empty 2s1 orbital, like half empty.
Uh-huh.
So, sir, both of the 2s1 orbitals combine to give us the full orbital,
Mm-hmm.
the one shown in this figure,
Mm-hmm.
or is it half full? As sir, like it is written, it's half full, but
Uh-huh.
in the diagram it is shown as full. So, sir, which one is right?
Where, which diagram you're talking? This diagram which you're seeing at the screen now, or other diagram?
No, sir, the one I'm seeing on my screen. In the graph, it is shown as full,
Uh,
but in the text, it is written as half full.
in the graph, full means, see, half full means, actually, see, what is happening is that all these are actually this is all these energy levels which are being shown here, they are forming actually the 2s band. So when I'm saying it is half full, 2s band is half full, like half of the energy levels which are there in the 2s band, they are occupied, rest half are actually empty. So where it is written, actually, let me see. The 2s band is therefore only half full. See, there is a difference between band and the energy level. These energy levels are full, right? The one energy level can have only two electrons. So we have n by 2 energy levels which are full, and there are n by 2 energy levels which are half full. Because when you have n lithium atoms coming together, total number of energy levels will be n, right? But we have only n number of electrons which will be occupied in the n by 2 energy levels. N by 2 energy levels will remain empty. Was that your question, or I did not answer your question?
So this was my question.
It's fine.
Yes, sir. So, sir, it is kind of attracting like how that helium molecule did, like forming various energy levels.
See, actually, it is somewhat like hydrogen, because in helium, both the energy levels were full, right? Here, when we formed like there were two 1s electrons in each helium. When they interacted, they formed two molecular orbitals, and both the molecular orbitals were full. So basically, we can also say that both the energy levels were completely full. In case of hydrogen, it was happening like when the two hydrogen atoms came together, they had only one s electron, and then they formed two energy levels as the interaction of as the overlap of two 1s electrons. They formed one bonding orbital and one anti-bonding orbital, or we can also say that they formed two energy levels, and only one of the energy levels was completely occupied, and one energy level was free. So this one energy level is completely empty, right? We can still have more electrons in this, but one is fully occupied. Similarly, in this case, what is happening is that there are n molecular orbitals or n different energy levels, and only n by 2 of them are occupied by n number of electrons, and n by 2 are empty states,
Okay, sir, I
empty
got
energy
it.
levels.
Thank you.
Right?
Yes, sir.
Okay, thank you. Any other question? Any other doubts or questions? This is very important actually what we are discussing now, because This concept will be used much in this chapter quite a lot. Essentially, what you need to understand is that when n number of atoms, when they are coming together, they will form n number of energy levels, right? And based on the number of electrons in the original atom, some of them will be occupied and some of them will be empty. For example, in case of lithium, there were n electrons in the 2s band, right? So only half of the energy levels which are formed, they will be occupied, and half of the energy levels will be empty, right? And in case of another important thing is that because number n, or the number of atoms, is very high, like is of the order of 10 to the power 23, and they have to occupy energy levels in a range of 10 electron volt only. So that's why the energy levels are very close to each other. So practically, for all practical purposes, it becomes a continuous band, because there is a very high number of energy levels in a very small energy gap, right? So it becomes a continuous band. Another important concept was that there can be overlap of different bands, right? 2s band, the top of the 2s band can overlap with the bottom of the 2p band, right? So there can be overlap, and because of that, the transition of electron from one state to another state is very smooth. It does not have to jump actually a large energy gap. It can easily go from one state to another state, because energy wise it is very close to each other, right? And like that, in a gradual manner, it can go up to even vacuum level, right? So that is why, and this is the typical property of a metal. We will see in in the in like in next classes, that in semiconductors and other metals this is not the case. There is no overlapping of these kind of bands. It happens only in case of metals, right? That's why actually in metals, electrons are free to move around in the whole crystal, because they are not localized. They can go from one energy level to another energy level very easily, right? So that's why they are free to move around in the whole crystal. Electrons don't belong to a particular atom. They belong, each electron belongs to the whole crystal, in case of only, and that is true only in case of a metal. In language of quantum mechanics, we can say that electrons are not localized. They are actually free to move around in the whole crystal, right? And this is actually something very simple, actually, which we might have seen earlier also. We saw that there are only half of the energy levels which are occupied, and above that there are empty energy levels, right? So if for the definition of Fermi energy comes from this concept. Fermi energy is actually the energy level up to which all the levels are occupied. You can see this here. Fermi energy is taken from the bottom of the band, and all the energy levels up to Fermi energy EF0, those are full actually. So this, for example, here in this case, the electrons are occupying the energy states up to this energy. So that's why this will become the Fermi energy. And we will see actually Fermi energy is a very, very important property. It defines a lot of other properties of a material also, especially the electronic properties. So Fermi energy, the definition of Fermi energy is the energy level up to which all the energy levels are occupied, right? All the electrons pair up their spin and fill each energy level up to Fermi energy, which is known as Fermi level at 0 Kelvin. The top of the band is the vacuum level, where the electron is free from the solid, which means potential energy is 0. So the energy which is required to excite an electron from Fermi energy to the vacuum level, that is called the work function of a material. So basically, if you want to make an electron free from a solid, you will have to give the amount of energy which should be equal to the work function of the material. Okay. Work function of the material of the metal is the amount of energy which is required to free an electron from the Fermi energy level. Those are some simple definitions which can be useful later. This is just a table which is giving values of Fermi energy and work function for different metals. The higher the work function, that means the higher is the amount of energy which will be required for freeing up the electron from Fermi energy level. There is a question: why in this class slide electrons are occupied in more than half space? I explained this earlier. I think your question is about this: why the electrons are occupied in more than half space? Because actually the energy levels are not uniformly distributed. Energy levels, they are not uniformly distributed. So maybe the n by 2 energy levels are coming up to this energy level. N by 2, the number of energy levels will be same. It will be this much energy range will have n by 2 energy levels, and this will also have n by 2 energy levels. Okay, so although it is not half, because actually the energy levels are not uniformly spaced. Okay, I think it is already almost 10. So if you have any short question, we can address it now. Otherwise, please, I mean, today when you go back, look at these slides again, and try to see if you have any doubts, because these are very important concepts which will be used later also. And one important announcement: we will have a class on Saturday, because this Saturday is working Tuesday. So we will have a class at the same time at 9 o'clock. I will send a separate meeting invite for that, for the class, because yeah, it is not in this series of meetings. So I will send a meeting link for the Tuesday's class. Okay, if anyone has any question, you can, I mean, short question, you can write them up now, or you can unmute yourself and ask. Otherwise, yeah, I think we are done for today. It is already time, and we may have the next class also. Thank you. There will be no tutorial on Saturday. There will be no tutorials. Tutorial will be, as on only on the regular days. Saturday we will have a class. All right. Thank you, everyone.